Right. Okay, so chemical change, new substances are formed, physical changes, change in phase, no new substance is formed. A physical change does not change the set of chemicals involved. So, for example, in a chemical change, or in a physical change, you don't have like reactants to products, but you might have something like H2O in liquid form plus heat going to H2O in gas form. So we see changes of state, but our actual substance itself does not change. And then we've got some really nice examples of that down here. So like crushing a can, melting an ice cube. So again, this is just water changing states, boiling water, mixing sand and water, breaking glass, dissolving sugar in water. So that sometimes can be something that looks like it might be a chemical change, but it's a physical change. Shredding paper, chopping wood, mixing red and green marbles, sublimation. So that's a state change from a solid directly to a gas of dry ice. Oh, we were talking this morning actually about sublimation. Have you guys heard in Texas how people are saying that the snow is fake? Has anybody heard that? Yeah. Okay. So people are like, the snow is fake. And then they're putting like torches to it and showing that it doesn't melt into a liquid. But apparently what they're actually doing is, you know how we talked yesterday about, or the day before yesterday, about how you can go between solids, liquids, and gases. And often we see things just going between these, but we don't as often see solids going directly to gases or gases going directly to solids. But sublimation is when we see a solid go directly to a gas. So what people are doing when they're heating the snow up, in these videos that are going around right now, is they're sublimating the snow. So it's going directly from a solid to a gas. So it doesn't look like it's pooling into water. It's actually sublimating. So it is real snow. Texas has snow. How relevant that that was our like morning discussion. Okay. Yeah, so important notes on chemical changes are often accompanied by physical changes. Just as a side point. And then we're going to talk about a few other differences between pure substances and mixtures. Okay, so boiling point is the temperature which matter changes from a liquid. And what we're going to start seeing often is liquid abbreviated as a little cursive L in brackets to a gas. And I'm just going to do that as well. We often will put gas just as a little g, lowercase g in brackets, as heat is added. So heat is added, we go from a liquid into a gas. That's our boiling point. Condensation point is the temperature at which matter changes from a gas to a liquid as heat is removed. Okay, and then melting point is another difference here. Some other differences between pure substances and mixtures. So melting point, temperature at which matter changes. So these are just all changes in matter from a solid And solid, I'm just going to add this one. We're going to put in brackets often as like a little s. To a liquid. And are we adding heat or taking away heat when we're going from solid to liquid? Yeah, totally. Added. Okay, freezing point, temperature at which matter changes from a liquid to a solid as heat is removed. So heat is going from whatever it is, like away from water into the atmosphere, into its surroundings. Heat is being taken away, and our actual matter, our water, whatever it is going into a solid form or ice. And then this is a little graph that shows this. So what we get is as heat increases, so heat is increasing along here. So it's starting small, getting bigger, and increase in temperature is on this side here. Do we all know the difference between temperature and heat? Did we talk about that? No. Okay, temperature is average kinetic energy of a substance. So it's like you've got a bunch of molecules. You take the kinetic energy of all of them and divide them by the number of molecules you have. That's temperature. Heat is the total kinetic energy in a system. So you're adding all of the kinetic energy together. You're not averaging out or dividing it. You're just adding it all together. Okay, so as the total kinetic energy in a system increases and the average kinetic energy in that substance increases, at first we're going to see something as a solid, and then the temperature of our substance is going to go up as we heat it, and it's going to move from a solid to a liquid over some amount of time, and then it's going to be moving into a liquid. Vaporization is liquid to gas. So just as we're increasing the heat in a system, our temperature of our substance is increasing, and we're going up through these different stages. And then the opposite we can also do as we decrease the kinetic energy, the heat around it. So this is this actually should say increase in heat like around our substance. Technically, because this is like we've got like an ice cube, we're increasing the heat around it, like in the air around it, as we go this way. And then this increase in temperature is the increase in temperature within whatever it is that we are actually looking at. So the ice or whatever it is. So as you increase the heat around it, it's going to go solid, liquid, gas. As you decrease, it's going to go from gas to liquid to solid. Okay, so looking at this above graph, so we're going to just interpret this a little bit more. On the sloping portions of the graph, so on those parts that are sloping, all of the heat is being used to warm the substance. So all of the heat on these parts that are sloping is actually going into that substance and warming it up. Pardon? Warm. Yeah. I kind of crammed that into a small space. Warm the substance. So the temperature of our actual object, whatever it is, rises. Make sense? And then the increased energy causes our particles within it to move faster. So we know that within a solid, we've got molecules that they're not really moving around each other. They're just kind of vibrating in place. And then a liquid, they're sliding around each other. And in a gas, they're just like all over the place. So the increased energy is causing our particles to move faster. Therefore, the average energy of our substance, so the temperature, which is our average kinetic energy of the particles, increases. On the level portions of the graph, so this is sloping. This is those straight lines. So like right here. So kind of underlined slope and squared level. So on the level portions of the graph, the substance contains so much heat energy that it actually can't absorb more heat. Sorry, which part? Level? Level. Yeah, sorry, I just was differentiating like this paragraph or these two bullet points apply to the sloped portions, and then this bullet point applies to the level portion of the graph. So on those level portions, as we can see, the temperature of our actual substance, if we're talking about water, the temperature of it isn't actually increasing. It can't absorb more heat at that point. So it's just staying the same temperature, even though the heat of the surroundings is increasing. Can I flip the page? Okay, this is still to do with the level portion. Let's do the level portions. So all of that energy is used to cause particles to break apart. Oh, sorry, do you want me to go back? Yeah. So it can't absorb more heat. Oh, this part? Oh, the next, yes, this? Oh, okay. Yeah, we're caught up. Okay. Okay, so all the energy is used to cause the particles to actually break apart. So they're moving away from each other. And the substance is then going to change state. So this is just a much more scientific explanation of the state changes that we've talked about before, and the state changes that you may have seen in your other science classes. Okay. Now, pure substances, they actually have a constant boiling point. So this is, hey. So what's an example of a pure substance that you all have seen? Water, yeah. Any other ones from sodium? Yeah. Awesome. So pure substances, which can be solutions or they can be elements, they have got a constant boiling point. Mixtures, by contrast, ordinarily do not. So they usually do not have a constant boiling point. So constant boiling point just means that it has a point at which it boils, and then it does not absorb any more. It doesn't have any change in temperature. It's just boiling at that point, and turning into a gas. Whereas if you don't have a constant boiling point, you are still changing temperature. Your temperature is still increasing as you're turning into a gas. Okay, so this is that on a graph. Our change in state is starting at here. So this is where we're going from liquid to gas. And then as we can see, a pure substance, so water, as we increase the heat and it's changing temperature, the boiling point remains the same. So it's boiling all along here. And that's constant. It doesn't change. It's turning into a gas, but the temperature isn't increasing. Now, salt water is a mixture. And as it is boiling, as it's turning into a gas, the temperature of it is actually still increasing. So it's a little bit different. And we'll talk about how we can interpret that a little bit more. Okay, so looking at that graph, we can see that pure substances and mixtures are affected differently by their increase or decrease in temperature. Have you all made pasta before? Do you all add salt to the water when you make pasta? Yeah. And do you know why you do that? To make it boil faster? Okay, that is the one of the most common mixture pure substance myths. What you're actually doing is really useful. It's a really good thing to do. So normally water boils at around 100 degrees Celsius, right? But if you add salt to it, it actually increases the boiling point. So it does take a little bit longer to boil, but it boils at a higher temperature, and this does depend. It does depend on how much salt's in it, obviously, but it boils at a higher temperature. So then whatever you put into it is actually going to cook faster because it's in a hotter liquid. So that's kind of cool. And this is actually something that you can apply at altitude, because do you all know that at higher altitudes, water boils at a lower temperature? So the higher you go, the lower temperature water boils at, just because there's not as much pressure down on it, so it takes less heat for it to turn into a gas. So if you put salt water in it, you can get it up to a higher, or if you put salt in it, you can get it to a higher temperature and cook things at a higher temperature. So fun fact, kind of side tangent, but interesting. Okay, so when a solution of salt water is boiled, the temperature gradually rises as the water boils away. So basically, as the water is boiling away, you're getting an increased concentration of salt in that water, and the boiling point is actually getting higher and higher. So we're increasing in temperature. But if you boil pure water, the temperature will remain constant. So if you've got a thermometer in this, it is going to stay at 100 degrees Celsius that whole time. From when you first start boiling until when it all disappears. This is another word that I always struggle with because I always want to put two S's and one P for some reason. Okay, so similar differences between mixtures and pure substances are observed when they freeze. So again, pure substances have got constant freezing points. So when does water freeze? What temperature? 0 degrees. And when they melt, they have got constant melting points. And then mixtures, they can change. They don't necessarily always have the same freezing points or melting points. And salt water is another example of that. Kind of same thing as that graph up top, but in reverse will happen. Density is also another characteristic that we can use in order to determine whether something's a pure substance. So all pure substances have a constant density. So for example, water has a density of 1 gram per milliliter. And that will always be true of pure water. When we did our density lab with salt water, was it always 1 gram per milliliter, or did the densities change? It was different because we had mixtures, not pure substances. Okay. Any questions about that information? All right. So what I'm going to get us to work on, there's some questions here, page 61. There's a worksheet on phase changes, another one on properties of matter. So I'm going to put those up on the front table here. And I'm going to ask people to work on those for right now. While you're working on those, I'm going to come around and chat with you about your labs from yesterday if you did the lab. If you didn't, yeah, do it. Don't worry about it. Just work on those things. And then after that, we will... Oh, it's somebody chipping the ice outside. I was like, is somebody banging on the door? What's going on? After that, what we're going to do